In this lecture, I'll cover an example for showing column strength check. The example is a leaning column frame. As you see, this exterior column, top hinged, bottom also hinged. So this two exterior column has no lateral rigidity. So in this frame, this central column at the top is rigidly connected, so this central column provides lateral rigidity of this frame system. When you calculate strength of this column, we have to consider leaning effect. We assume the beam is fully braced against lateral torsional buckling. From now on, let's look at the column strength calculation of this one. We consider the applied load. So finally, we check the column strength. It is enough or not. So load condition like this: dead load, live load, and wind load. Load combination, there are 5. In this example, we calculate for 2 critical load case 2 and load case 4. In load case 2, we have just only vertical load. If we draw the moment diagram like that, we have the moment at the beam, but we don't have any moment at the column. So in that case, if we analyze this one, okay, center column reaction is 182. Exterior column is this one. So it is some reaction. That means column force, column axial force. Okay, we calculate column strength. So compare these two values. Column strength must be greater than this axial force. Then we can say this is safe for this loading case, right? In order to determine column strength, we have to calculate K factor, right? Effective length factor. In order to calculate effective length factor, we have to consider K factor modification. Firstly, we have to consider inelastic stiffness reduction factor. Let's calculate PU over PY. Column yield strength, PU is the axial force. That is 0.253. It is less than 1/3. That means there is no inelastic stiffness reduction, so tau equal 1. And let's calculate the K factor. As you see, bottom of this column is hinged. The stiffness ratio is column strength over beam strength, right? So we have a certain value of column strength, but we don't have any beam stiffness because it is hinged or connected. So stiffness ratio GC equal infinite. But in this real world, there is no infinite case. That means there is some friction here, a little friction. So in design practice, we use G equal 10 instead of infinite. So GC adjusted is equal to 10. To account for far end hinge of the beam, let's look at from here to far end of the beam. It is not rigidly connected. It is hinged, right? So we have to adjust LG prime. We have to use LG prime. So far end hinge case of unbraced frame equal original beam length. Original beam length is 40. You find the hinge case, we have to use times 2. So LG prime must be we have to use 80. Then let's calculate the stiffness ratio at the top here. At nominator, we have to use column I divided by column length. This is a beam I divided by LG prime, right? You have 2 beam, left hand side and right hand side. As you see here, we have 2, 1, 2. So there is 2. The value is 0.44. So from this frame is unbraced case, we have side sway. You have GC 10, GD 0.44. From the alignment chart of unbraced case, you can get Kx equal 1.73. That is K factor. Now you have to consider the leaning effect. As I mentioned, this exterior column leaning interior column. So this interior column become weaker. Become weaker means the K factor become bigger due to leaning effect. Original K factor is 1.73. If you calculate this leaning effect, Kx prime equal, do you remember the equation? Square root of the total vertical load. Total vertical load is this one. The actual force of that interested column, interior column, that is 182. I1 is moment of inertia of interior column, 7 to 3. This II over Ki square, II is interior column, Ki square is interior column's K factor. Because only one column, interior column, has lateral rigidity. So in this calculation, we just use just one, okay, interior column. If there are several columns that has the lateral rigidity, we have to add together those columns. Do you understand? Let's calculate the slenderness parameter. So lambda Cx pi rx kxl square root fie. Kx is this one, 2.19, L 20, 12 convert in inch, pi radius of gyration in strong axis, square root to fie value. That is 0.981. It is less than 1.5. Okay, let's look at. There is some typo here. That is 5 over 8, not 50 times 1.73. And then regarding the weak axis bending, weak axis direction, we have lateral support. There is no lateral sway. So K value is 1. And 20, the length. And then radius dilation in weak axis, like that, 1.09, less than 1.5. If we compare the strong axis slenderness parameter and weak axis, the weak axis we have the bigger value. Then weak axis governs the column strength. So the slenderness parameter is less than 1.5. So we have to use this equation. ASFI 0.658 lambda square. So if you input this value 1.09 square something, then you have that value. We apply pi c 372. That is column strength. The actual force is 182. The ratio is less than 0.5. So this column is safe for that load case 2. It is simple one. And then let's check the load combination 4. We have the vertical load, dead load and live load, and then we have the lateral load due to wind load. Like that. That is vertical load and then wind load. Like that. Check the adequacy of column CD, this column, interior column. So we already calculate PN, right? The PN calculation is the same as that load case 2, load combination 2. Okay? The procedure is identical. PN is this one. Then what should we do from now on? Let's consider this one. We have to check this one. Pi PN PU plus pi MN MU, right? There is some parameter alpha beta depending on the magnitude of PU over PN, right? That must be less than 1.0. So far we get PU, right? And then you get pi PN, right? So from now on, we have to calculate MN and MU. So I will show you some procedure how to calculate MN, MU. Let's firstly calculate MN, moment capacity of the central column. Let's look at the analysis result. The sway frame case, we have to calculate the moment separately. Do you remember? That is non-sway case and then sway case. In non-sway case, we support laterally here. We have to apply the loading, vertical load and lateral load together. But this lateral load is supported by this assumed some lateral support. In this case, it is symmetric, left and right. So in non-sway case analysis, this result or without any lateral support and apply the vertical load, then we have the same result because left and right hand side are symmetric frame. In non-sway case, we just apply the vertical load. And then sway case, we applied lateral load like that. Let's calculate the MN moment capacity of this column first. Yeah, this MN you already learned MN of the member in undergraduate steel design course. So I assume you already know how to calculate MN. So I just quickly go through. Okay, LP equal 10.3. You can get this value from the AISC specification, and then LR, LB, then your B, this one. It is braced top and bottom. Your braced length of this column is 20. So LB is greater than LP, less than LR. In that case, and then CB determines as. You have to calculate CB, right? Yeah. So M maximum moment is 208. Here, as you see, column moment maximum is 208, right? And MA, 1/4 point. That means you divide like that, 1/3 point. That is MA, midpoint MB. This one is MC, right? MA, MB, MC. Then you can calculate CB from this equation. Then you can get 1.67. So 5B MP, 5B MR, you can get from the AISC table, design table. Then you can calculate 5B MN equal CB. That is the equation. So you can get this value. And then you can compare 5B MP. Oh, this value is greater than 5B MP. You have to use 5B MN is 311. The moment capacity cannot be greater than full plastic moment capacity, right? So you have to use this one. Lastly, we have to calculate mu. We already learned how to calculate mu, right? Previous lectures. Do you remember? Mu equal B1 MNT plus B2 MLT. B2 MNT MLT, right? Here, this is MNT, this is MNT, this is MLT. Because the moment without side sway, no translation. Moment, lateral translation. As you see, MNT of this column equals 0, right? There is no moment. We just have the moment in case of lateral translation case, lateral sway case. The maximum moment is 208 of the column. Then let's go. Let's calculate B1 first. That equation CM equal 0.6 minus 0.4, and so maximum moment is 208 at the top. Bottom, the moment is 0. Larger one or smaller one. Then CM equal 0.6, right? And then let's calculate GC, adjust to 10, okay? LG prime, brace case, far and hinge, in that case the adjusted factor is 1.5. Then 26.7, so GD, we calculate stiffness ratio. You see here, brace case. At the bottom, that is the infinite. For design purpose, we use G equal 10, right? At the top, you have to calculate the stiffness ratio of column of a beam, right? So that equation, like the column stiffness, beam stiffness, modified L, right? Yeah. So then you have 10 and 0.148. In that case, braced case. So in alignment chart, from alignment chart of brace case, you can get Kx equal 0.73. And then let's calculate PE1. PE1 is the brace case Euler working load, right? So here, pi square EI over KL square. That is the equation, right? So if you calculate this value, K equal 0.73 L20 inch pi square EI, then you can get this value. So B1 equals CM over 1 minus PU PE1. So CM equals 0.6, 1 in this brace case, 94. So 94 and PE1, this value here, and you can get 0.608. It is less than 1.0. as you know, B1 is amplification factor. Your calculate amplification factor is less than 1.0. That means moment does not amplify in case of nonlinear analysis. Of course, there is no moment. So B1 M and T column moment equals 0. So whatever which value we have for B1, this calculation must be 0. But I just show how to calculate B1. So B1 value is less than 1.0 means let's assume we have the moment like that. We have moment like that. If we calculate less than 1.0 means the amplified moment, if you do nonlinear analysis, this is maximum moment. Then moment less than this maximum moment. Amplify the moment a little bigger like that, but it is less than this maximum moment. In that case, the B1 is less than 1.0. Then, in that case, what is the maximum moment? This one is the maximum moment, right? Then we just use first order analysis result, linear analysis result. Just use this value if B1 is less than 1. And let's look at. So we calculate B1 and let's calculate B2. B2, the equation is this one. We have to use the total vertical load PU. Total vertical load is this one, 150.4. And then the KX is 1.73. We already calculate previously. And then PE2 1.73 and L pi square E I. Then we have this value. The summation of the load is this one. So the calculate value is 1.14. That is B2. So mu equal B1 MNT plus B2 MLT. B1 equal 1, 0 plus 1.14. The moment is 208, this moment. Then resulting mu is 238. Okay? So this value, your calculate value is 0.253 is greater than 0.2. Then you have the equation this one. If it is less than 0.2, you have the different equation. This equation, you already calculate this value, 0.253 plus 89. mu x is this one. That is second order moment. So 238. M and T is previously you get 311. That value is 0.933. That is less than 1.0. This interaction equation is less than 1.0. So this member is safe. Adequate. You understand? See you everybody next week. Bye.